Alright, this is Algebraic Reasoning 1.3, Chapter 1.3. We are modeling with linear functions. So we're going to take the equations we've done so far, and we're going to build equations based upon real-world data. So this one right here, we have each year during the growing season, a tree grows larger by adding another layer of cells just beneath the bark. So, you know, trees have rings. So we've got... it's kind of like 1 ring, 2 ring, 3 ring, that sort of thing. And this has to do with the size of the tree rings. All right. So when there's plenty of rain, the trees go. However, it says not all tree rings have the same width. Some trees grow more where there's lots of rain and the soil is fertile. And we can draw conclusions about the temperature of rainfall for a particular year based upon the width of a tree ring. Okay, so basically here's what happened. Mariette measured the width of tree rings from the core sample she took from a post oak tree in the Brazos River Valley in central Texas. Basically, she took a sample of a tree in Texas, and she measured the tree rings, right? And she calculated the radius of the tree, and here is her result. So on year 0, it was 2.5 centimeters wide. That was the radius. On year 1, 2001, the radius was 3.1, then 3.5, 3.9, 4.4, and we're going to start calculating the difference. So first things first, let's calculate the difference. Up here, every year, we are simply adding 1, adding 1, adding 1, adding 1, adding 1, adding 1. Okay, so that's consistent. And so let's look at the bottom. So we do 3.1 minus 2.5, we get 0.6. So for the first one we added 0.6. And then we've got 3.5 minus 3.1. So the second one we added 0.4. So we already know these aren't perfect. And then I'm just going to fill these in right quick. So here we go. We got 0.6, 0.4, 0.4, 0.5, 0.5, and 0.6. And we will notice they're different. So based upon what we've done so far, we would say this is not a linear function. However, in the real world, not everything is perfect. All right. If you notice, these are actually really, really close. So what we're going to do here is we are going to find the average rate of change. We are going to average those differences together to find a general rate of change. So in this case, the way you find an average, remember, add them all up and divide by how many there are. So we've got to find the average rate of change, average change in y. So that the average, I'll put average change in y equals, we're going to do 0.6 plus 0.4 plus 0.4 plus 0.5 plus 0.5 plus 0.6. And we're going to divide it by, there's 1, 2, 3, 4, 5, 6, divided by 6. So the average change in y is going to equal, the average change in y equals 0.5. I'm not even round, that's the average change in y. So, to get our slope, we'll take the average change in y, we'll take the change in y divided by the change in x, which we did our average, that's 0.5, divided by 1, which is 0.5. So I'll go write it over on the right side. So in this case, y equals 0.5x. And our starting point was 2.5, so plus 2.5. Now, again, this is not perfect because we had to average our spot right there. But this is going to give us a general understanding of what's going on. And I think they give us a chart down here. Actually, no, they didn't. If we scan down, we're going to find this chart right here, which basically what this is, these are the same years. So again, every year went up by 1. So plus 1, plus 1, plus 1, plus 1. This is just a little further away down your chart, so pause until you find it. And these are the same radius down here. So this is the same tree we're measuring. And then they use the radius to find the circumference of the tree at any given year. And the circumference they really can use to find the age and really how old it is and things along those lines. So what they did is they took the radius. Remember, if you remember, the circumference of a circle is 2 pi r. So they took the radius. So for the first year, they took 2.5, and they multiplied it by 2 pi, and they got 15 pi 7. Then they took 3.1, multiplied it by 2 pi, and got 19.5, so on and so forth. And they wrote a graph on this one. So let's go ahead and do this one as well, just like we did it before, and find our differences and go. So 19.5 minus 15.7, so 19.5 minus 15.7, we get 3.8. So we added 3.8. And then I'm going to pause the video and fill in the rest of these right quick. All right, so we got those differences right there. And again, we can use those differences to find an average change in y. So the average change in y, whenever we put a bar over it, things like that, that typically means average, is going to equal, add them all up and divide by how many there are. So that's 3.8 plus 2.5 plus 2.5 plus 3.1 plus 3.2 plus 3.7, 3.7, and we're going to divide all of that by, there's 1, 2, 3, 4, 5, 6 of them, and we're going to get the average change in y equals 3.1. Now you get 3.13333333333. Yes, but I just rounded it off. I know you got a whole bunch of threes, but we just rounded it to 1. So again, change in y divided by change in x, which was 1. That's our slope. So in this case, y equals 3.1x, and then your starting point of 15.7 plus 15.7. That would be an equation that models the circumference of a tree based upon a year. The reason I can say it models the circumference based upon the year, remember the x value, what we put in for x, was the year number, and the y that gets spat out is the circumference. These are the y's. So if I plug in a 4, I get 27.6. If I plug in a 6, I get 34.5. Or actually, in this case, I get really close. Because we used an average y, it's not going to be perfect, but it's going to get really close. And to illustrate that right quick, let me scroll down. And they actually plotted these guys. All right? This is what that graph looked like. 15.7, 3.13x, and 15.7. Okay, so they rounded to the second decimal point. But still, that was the same equation that we got. They just rounded to 2 decimal places instead of 1. And when you graph it, that line fits that data really, really good. So again, it's not perfect, but it is an excellent estimator of what's going on. And that is what we're going to be doing through this chapter. Using the data that's given to us, find an average rate of change, and find a line of best fit based upon the averages.